Everyone, to our Data Seminar or AI Institute seminar. Today we welcome our own Andrei Klishin, who is a postdoc scholar at the AI Institute. He working with me and Nathan. He joined us from University of Michigan, where he did his PhD, and University of Pennsylvania, where he did a postdoc. So his background is in physics and statistical mechanics, and hopefully you get some ideas on how to use these kinds of statistical mechanics tools to analyze machine learning algorithms from the talk. So take it away.
Great, thank you. Thanks for having me present. I'm currently still at UW. There will be an announcement, which, well, most of you know already, where I'm going next, but that's at the end. But first, let's talk about the fun science part. So we are here, it's a data-driven seminar, like we like data-driven methods. There is a lot of kind of philosophical takes on what data-driven methods are like. Here is one philosophical take that I like on data-driven methods, written by our very own Nathan and Steve, who are not with us in person, but with us in the spirit today, that they wrote in Nonlinear Dynamics in 2022, with this pretentious title, Parsimony as the Ultimate Regularizer for Physics-Informed Machine Learning. Very cool title, but basically they lay out the argument that, okay, we want to use machine learning and AI because it's, promising technology that is around, and we have different ways of sort of incorporating it into our workflow. And we have qualitatively two choices of what we can do. We can either let it learn new representations that are just beyond human comprehension. That's what a lot of neural networks by default do. They do all their backpropagation stuff and figure out something in the weight combinations that captures training data. Or we can try to constrain these machine learning systems to physics understanding, and specifically to parsimony, to some measure of simplicity of the physical behavior. And well, here's Nathan. I need to acknowledge him because he's one of my postdoc advisors. And that's nice, of course. I like the argument. Of course, I'm leaning towards the second part because that would allow us to do stuff simpler and hopefully generalize better. But I have an issue with that statement, specifically this word physics, because that word doesn't mean what I think that word means. Because I have all the physics degrees and hang out around physics departments. And this word was used by people who are not spending most of their time in physics departments. So physics in machine learning context very often means things like ODE or PD dynamics or symmetries or conservation laws. Yes, we can constrain our machine learning system to predict some sort of dynamics. But that's not all that physics allows you to do. You can kind of dig deeper if you just happen to have access to other conceptual tools. And because I've been studying statistical mechanics for a while, I think of physics in terms of energy landscapes and collective behaviors and phase transitions and stuff like that. So that's sort of what I immediately started looking for. And when I showed up here and I started my job here, I was like, okay, what kind of problems do you guys have? And people told me a couple different problems. And I want to tell you two stories today. One story is about system identification, basically asking under what conditions can you pull out ODE from trajectory data, which is Cindy, essentially. And the other question is about sparse sensing. Sometimes we can reconstruct complex high-dimensional data sets from sparse measurements, but we need to place sensors in a clever way. So what drives that clever way of placement? So I'll go through them sequentially. And we start, of course, with Cindy, the original 2016 formulation. We say you observe some sort of trajectory of a system x of t. You just have a bunch of snapshots. You maybe numerically compute derivative from it, x dot. And you want to know what is the dynamical equation that specifies that trajectory. If I were to say that x dot equals f of x, what is that f? And the idea of Cindy is you want to simplify it, turn it into linear regression, but to also capture nonlinear dynamics at the same time. So you come up with an overcomplete nonlinear library of a bunch of functions, a bunch of nonlinear functions of x, which are typically taken to be some sort of low-order polynomial expansion, like x1, x2, x3, constant term 1, or different combinations like x1 times x2, or x1 squared, or x1 cubed times x2 to the 7, or whatever. And you want to combine them in a linear fashion with some coefficient xi, and they carry around a bunch of indices. The main thing, you want this combination xi to be sparse in some way. And there are different ways that you can measure sparsity or promote sparsity. And the most direct measure of sparsity is how many terms did I use. So how many of these xi's are strictly not zero. I don't care about magnitude, just how many are non-zero. And this is called the L0 pseudonorm. It's a pseudonorm, not a real norm, because it doesn't scale if you rescale the values. But anyway, we would like to optimize for L0 norm to be small. It's hard to do directly, so we do all kind of proxies. So here is how the regional SINDI works. You guess some sort of training data from some system. We all like Lawrence. Everyone benchmarks on Lawrence all the time, and so I will as well. And you get this dense vectors of what is your x dot, y dot, z dot of time. And then you compute a library of a bunch of polynomial terms, and then you do regression, and then you cut away all the terms where the coefficients are below a certain threshold, and you do it iteratively, sort of sequentially threshold at least squares, and then you get some sort of model where the numbers on the coefficients that you get are hopefully close to reality. In practice, people say, okay, if it's minus 9.9996, and in reality it should be minus 10, that's good enough, right? We don't need to worry about the discrepancy. Well, I will worry about the discrepancy in a little bit. But then you get some sort of system, you identified some equations, and you just integrate it forward, and you're cool, right? And you hopefully get something similar. I want to stop here for a second, actually, because we just said integrate forward the Lorentz system. That's actually kind of a hard thing. Like, who integrated the Lorentz system? Why do we have such a notion as integrating the Lorentz system? And you would be like, duh, Lorentz did, right? Here is the paper, right? It has one author, Edward Lorentz, 1963, a meteorologist from MIT. And Edward Lorentz, not to give him credit, Lorentz system of equations is a very clever reduced order model, but one that he came up with manually, sort of a very invasive kind. He looked at a fancy convection PDE and was like, oh, we can actually describe it in terms of just 3 variables. But when it came to integrating that, if you just look at acknowledgements, it says the writer is indebted to a colleague, and then special thanks are due to Miss Ellen Fetter for handling the many numerical computations and preparing the graphical presentations of numerical material, which means doing all the computing and plotting, which apparently as a man he couldn't be bothered to do, and he couldn't be bothered, at least in the 60s, to give her credit, put her as a co-author of the paper, which in modern day, by modern standards of scientific credit, would obviously happen. Lawrence did it several times, as was the theme, the way to do in the 60s. And a different paper, he acknowledges Mrs. Margaret Hamilton, who later did a lot of numerical computations to land rockets on the moon, which is numerically hard problem. And there's this wonderful article called The Hidden Heroines of Chaos, published in Quantum magazine by Joshua Sokol, 2019, that digs deeper into the story, and also who decided to dig into it, who decided to acknowledge them, and what happened to Ellen Fetter and to Margaret Hamilton later on. I highly encourage you to read. But OK, now we also learn how to just abstract it out. And if I want to integrate forward Lorentz equations, I just stick them into ODE integrator, and the computer does it for me. Great. So now that we can do it very reliably, what have people been doing about SINDI? I showed you the 2016 version. That is the most basic take. There has been a lot of updates, of course, a lot of different variations. Of course, once you find your ODEs, you can try to find your PDEs. There was a paper on that. You can find PDEs in a very parametric way. So Zach Nicolau did this thing where he had different pattern forming equations that, depending on the parameter, but keeping the same functional form, you have different patterns, and you want to figure out what the equation is. There's really cool developments in the weak form of SINDI, which basically replaces taking numerical derivatives with taking the weak form of derivative, which turns out to be much more robust to noise. This is work mostly from Dan Messenger and David Bortz from Boulder. They have a string of papers on it. There's work on discovering the proper coordinates to measure our dynamics by Kathleen Champion, and there's other follow-ups where you basically hook up SINDI together with an autoencoder to find the proper nonlinear transformation of coordinates in which your dynamics are going to be sparse. And more recently, there was a lot of interest in sort of uncertainty quantified versions of SINDI, based on things like ensemble resampling by Urban Fazal, who used to be a postdoc here some years ago, where you sort of do bootstrap resampling from the same trajectory to fit a bunch of Cindy models and have error bars that way. Or you can have sparsity promoting priors by Seth Hirsch and company, which also in some way lets you have the error bars. And broadly, a lot of Cindy questions revolve around minimizing some sort of loss function, and you pack it full of whatever things you want your model to have. So you say my best fit is argmin of a loss function. What do you put in loss function? And I stick in a whole bunch of arguments here, and it mainly, and I want to solve it in sort of simple case. So you have your least squares fit, so just x dot minus our best guess, which is the linear combination of nonlinear functions, plus some sort of regularizer on the coefficients of Cindy. We use LP norm with p less than or equal to 1. And this is a picture that is in every stats textbook. It's in none of physics textbooks. So that's something that I learned. That was very useful. What is the difference between different LP norms? That if you regularize with L2 norm, that means your coefficients just want to be small, kind of closer to 0, but they're not necessarily forced to sit on any one of the axes of the coefficient space. So none of them are necessarily 0, so you don't have sparsity. If you have L1 sparsity, or even better, if you could have L0 sparsity, you could force a bunch of In a second when I talk about uncertainty classification. But what we can do before that is start playing around with our Python parameters, specifically my sparsity penalty. So ways this free energy depend on the sparsity penalty actually has an incredibly simple function form. It's just f sub gamma plus lambda times size of gamma. Because I'm started talking about things per data point, I just switch everything to lowercase. But if you think of it as a function of lambda, that's a very simple function. That's a straight line, right? It has different intercepts and different slopes. So I can just draw a whole bunch of straight lines and ask which one has lowest free energy, which of those straight lines is lowest. And okay, I have 1,000 different sets. Well, I'm going to just draw 1,000 straight lines they sort of fan out. And for every value of lambda, I ask which of the straight lines is the lowest. And because it's just a bunch of straight lines, some of them might start a bit lower, but have steeper ascent, higher slope. Some of them start a bit higher, but have a smaller slope. So you can see this several discrete breaking points where your model shape switches between different forms. And this is very sort of nicely interpretable and practical, but not super useful because I don't know what sparsity penalty should be. I want to vary it very widely. So I need to put it in log scale. And I can just vary my sparsity penalty per data point across 10 orders of magnitude. You cannot really go much wider than that. And then you start seeing these different basins of where models of different shape have been identified. And you can see that there is fairly wide regions where my model shape is consistent and also corresponds to the correct shape that I expected to get. But that's what happens without noise. Well, this tells me that I can play around with sparsity parameter to discover a whole sort of set, a whole sequence of models of different sparsity. That was what happens without noise. What if we start putting on noise? I wrote down this formula for free energy. Basically, for every instantiation of the trajectory, I can deterministically compute what the free energy is. It's just the formula, you plug in your data, you get some number out. But the mapping from clean trajectory to noisy trajectory is stochastic. It has noise in it. It varies. So that means the corresponding free energy would also vary, sort of the goodness of it of different sets. So we can start drawing it as I start to gradually crank up the amount of noise. At every value of noise, I can compute, oh, let's say just like 10 realizations of free energy of every single set at that level of noise. And if my noise is very low, and it's obviously normalized to the variance of underlying data, if it's like under a couple percent, then my lowest free energy solution happens to be the correct solution. So my inference works, it tells me what I need to know. That's great. But as my noise gets higher and higher, my sort of correct answer starts overlapping with a range of free energies for other answers. And it's a range of free energies because it depends on noise realization, not just magnitude. So once I go beyond something like 6% of noise, my answer, my identified set of variables start depending on the realization of noise. Not just the magnitude, but the specific realization of noise in a given trajectory. And that means basically my inference is kind of worthless, right? It becomes super stochastic. It's also funny is that this breakdown works a bit differently for x dot and z dot, as opposed to y dot. For y dot, you trade off first a correct solution of 3 terms to a wrong solution of 3 terms. Whereas for x dot and z dot, you sort of go from correct directly to a much larger set. And when I was looking at this picture, and I already committed to this particular color map, I really like this color map, yellow into brown. I said, I saw this picture somewhere, except for it was not a science picture, it was not a science source, it was not in a paper, but where have I seen it? And then I realized it was this picture.
the scene from Mad Max Fury Road, a wonderful action movie from 2015, directed by George Miller, that I highly recommend to everyone. And if you haven't seen it, there is a scene where there is a convoy of a bunch of cars that drive into a sandstorm and get lost. And I thought it's very sort of fitting to have a similar picture, similar sort of many fronts of the sandstorm. You should go watch it, it's great. But what it means for us, we can start now talking about Cindy with uncertainty quantification and ask how does my uncertainty actually scale with inputs to Cindy. And the way we can do it is we can, well, once we fit some sort of best fit, sort of the posterior mean of distribution, I can just ask what is the residual? What is left-hand side minus right-hand side? So my empirical derivative minus the best guess of the model, what is the distribution of that? How does it look like if my noise is either fairly low or substantial? If my noise is very low, so left-hand side and right-hand side don't match because my derivative has numerical error, just finite difference error, which has different magnitude depending on where exactly you're on trajectory. We roughly know how it scales, but we can't really easily predict what it is at every point other than from a history. As my noise cranks up, this distribution becomes much nicer, much more Gaussian, but I still can always just empirically find what is rho, what is the width of this distribution, and set it to be my resolution parameter, and ask how does my resolution parameter scale with the amount of noise I have done on trajectory, and just plot it. And you see that there is sort of very well-defined boundary between the two regimes. In one case, if my noise is very low, my error is driven by systematic factors, by the fact that I'm very bad at taking derivatives because finite difference derivatives is not great, but we understand it pretty well. And so my resolution parameter stays fairly constant. So all error bars are going to be fairly constant. But then as I crank up the amount of noise, my resolution parameter starts being dominated by noise, and you can actually just propagate the amount of noise through the finite difference scheme and figure out what the noise on the measured derivative is going to be. But now that we know rho, we actually know how to properly scale from all of our posterior error bars, and we can just plot them. And because the Lorentz model happens to have just 7 variables, so I can just ask for each of the variables, how far off am I? So what is my confidence interval if I just subtract the correct answer? And if my noise is very low, you can see that my error bars are vanishing, they're not visible. But I have systematic difference between the correct answer and the answer that I infer. And if my noise is substantial, as in the bottom right picture, I have quite substantial error bars. So the correct answer is included within the error bar. But as I crank up data more and more, eventually my estimates all converge, my error bars shrink, and now I can see the actual systematic error. So to conclude on this part of the talk, I want to draw this kind of inference phase diagram. So in the space of all the parameters that affect Cindy, when does it work, when does it not work? And because in L0 sense, we cannot be a little bit, your model shape is it correct or wrong? Like it cannot be small. So we can have a very, very sharp discrete boundaries where inference succeeded or failed. And in the space of noise magnitude and sampling period, these two boundaries happen to be basically orthogonal to each other. So either you have correct identification, or you're limited by systematic error in case your finite difference gets really bad, or you're limited by noise on the other side. And in the space of noise magnitude and sparsity penalty, you can have situations in which you have correct number of terms, or if your sparsity penalty is too high, you start throwing out relevant terms. If your sparsity penalty is too low, then you end up with too many terms. And it's also interesting that there is sort of like a trade-off, some sort of power law that's happening there, is that as I crank up sparsity penalty, I can tolerate more and more noise to a point. Because the main sort of failure mode, when you start adding more and more noise to your data, Cindy is sort of desperately trying to fit this noise with something deterministic, and is really wanting to throw in more terms to fit it just a little bit better. But if you're more reluctant to throw in more terms, you can tolerate this onslaught of noise for a little bit. So overall, I told you that discrete selection converges exponentially if you have this L0 penalty properly implemented. Continuous inference converges as 1 over square root 10 up to systematic error. Sparsity penalty selects the model size, and we can have the whole hierarchy of models instead of just kind of pulling the sparsity penalty out of thin air. And with enough noise, more data will help. So all this phase diagrams have already like scaled out the amount of data. Of course, there's lots more things that you can do. You can dig deeper into the structure of the spin energy landscapes. You can have better algorithms than just brute forcing to design solutions. You can integrate it with any other Cindy features that have been done. You can import in discovery, denoising, weak form, parameter variation, and maybe dig into this scaling power laws. So maybe before I go to the second part, if there is a burning question in in-person audience or on Zoom on the Cindy.
So why don't we use like diffusion models for denoising the model, like denoising the data?
Well, first, if it is,
Can you repeat the question?
yeah, so the question was, why don't we use diffusion models to smooth out the data? And if you mean diffusion model as in like the deep neural network thing, like the generative AI, if you take that, that means you already gave up on razor and interpretability. Like that went out the window the moment you started. Why don't we denoise in general is because denoising, it reduces the amount of noise, but it introduces a systematic error. It's fairly well known that denoising variations of derivative skews the derivative. It basically pushes your signal to be like closer to zero, less varying. So your estimate of derivative is going to be systematic. So if you were to be actually, so on this top left plot, your horizontal axis is roughly a measure of systematic error. Your vertical axis is measure of random error. So if you crank up denoising, you might be able to sort of move down and to the right. Except for I don't know what slope. I don't know what exactly the trade-off is between random error and systematic error. But basically, most denoising approaches require you to introduce systematic error, which is kind of poorly understood. There are several approaches that try to do like system identification and denoising simultaneously. Again, they don't like to record the cases within break, so I don't know what you mentioned.
So like when we use Cindy, so every time, is it guaranteed that it won't break? Like how is the chance? How much of the chances we have that it will break? Or it is more like I would say protective towards the breaking the model, breaking the system.
Okay, so the question is, are we guaranteed that Cindy will break and under what conditions it will break? So here I was interested specifically on the limit of pretty large amount of data, right? So you can crank up noise. Noise gives you some amount of problems per data point, but it's the limit of number of data points going to some large number. And so you're basically margin where how much noise is required for breaking, that margin is continuously shrinking as your amount of data gets higher and higher. So in the limit of infinite data, it would be basically deterministic that below this amount of noise, you're correct. Above this amount of noise, you're wrong. Finding the exact threshold is hard because it's dependent on the problem that you're trying to fit, right? If you have finite amount of data, then there is sort of like a coexistence region where it would sometimes break, sometimes not. But you can think of it as like your probability of breaking against the amount of noise is sort of like a sigmoid, with the width of sigmoid driven by how much data you have. If infinite data, your sigmoid becomes a step function. Any other burning questions? So let's go to the second part.
Another you showed some results of compared the non-optimal sets you choose with the optimal sets. The free energy decays exponentially to those results, right?
So the free energy, so if you go to this picture, free energies of all sets scale roughly linearly with the amount of data. But the question always is, which set has the lowest free energy, right? So if you think about it in terms of intensive free energy, so capital F, so bottom left side, as you crank up the amount of data, your absolute free energy difference gets bigger and bigger and bigger between the best fit and the second best fit. Like all this dance around sort of free energy per data point is to learn what the asymptotics are. But basically, imagine you're trying to compare exponent of 5x with exponent of 4x. Which one of them is going to win? One of those is going to sort of diverge much faster, go away much faster.
Okay, the next page, results, yes, I noticed that there are some points do not decay as expected.
Yeah, so some don't decay exactly exponentially, and that's the ones that correspond to the faintest or most green color, and that's the ones that correspond to largest delta t. And large delta t means you have the highest amount of systematic error, and the systematic error starts messing around with the structure of the landscape quite a bit. But basically, once your delta t is small enough, then you fairly consistently identify the hierarchy of sensitivity. Okay, let's in the remaining time.
Andrei, just a sec, because they still can't hear you very well. Are you having your audio on? I think that would be.
Frame it once again as a Bayesian inference one. So similar Bayesian inversion, slightly different variables because I'm solving slightly different problem. And you can just solve it as the argmax of the top after you make some assumptions on what the forward model is and the prior is. And for the forward model, for the prior, we like to assume usually that we have a Gaussian prior that is fairly wide, with the variance of the Gaussian prior being either flat, like uniform, isotropic, or it might be driven by the singular values of the data set that we picked. On the other side, for the forward model, we assume that we have, again, Gaussian noise. So from the difference between proper sort of linear combination of modes that is subsampled and what we actually observe on the sensors is just Gaussian distributed. You combine those things, you put it in log likelihood, you try to solve it as argmax problem, and you find a prescription that for any measurement on the sensors Y, here is the reconstruction of the modes that you're supposed to get A. What matters here in this bulk expression is that there is some matrix that I need to invert. And technically, this reconstruction works for any input, it gives you a number. For any number of sensors, it would give an output. The question is, if my input fluctuates a little bit, how badly would my output fluctuate? So what's the sensitivity of this reconstruction process? And that depends on, is matrix A a kind of matrix that likes to be inverted? And there are different ways to quantify it. And the way we use it, we quantify it, we use a principle called de-optimal design, which is basically you're trying to minimize the volume of the posterior confidence ellipsoid, which means you want the determinant of this matrix to be as large as possible. Typically, matrices with large determinants, given the quantum size, are more invertible than, and there are some other design principles that people use in other constraints, in other situations, but that's the one we decided on. And we want to try to understand what does this determinant do? How does it behave? How does it depend on my selection of the sensors? And I would like to, determinant is like a combinatorial quantity, and it's going to quickly get very large as my dimension gets large. So let's put log on it. And again, because I'm a physicist and I don't like to maximize things, that sounds a bit gross to me. I'm going to minimize things by just sticking a minus in front of it. So I'm going to say that my landscape, that my target objective that I'm trying to optimize is negative log determinant of this matrix. And you can rewrite it a little bit by using this determinant properties as constant minus trace log of some matrix, in which the matrix that looks like identity plus stuff. And the stuff is positive definite addition. It always stays as a P by P matrix of variable rank, where adding stuff on the diagonal of that matrix is good because it makes my trace log larger. It makes my energy smaller. Putting stuff off diagonal is bad. That's a very qualitative intuition. We would like to turn it into something more quantitative. And also, once you have this objective, sort of if you were a mathematician, as some of my colleagues are, their intuition would be, how do I place sensors in some sort of greedy manner to guarantee that my greedy placement is, has some bounds, that it's not going to be too horrible. But I'm not a mathematician, I'm a physicist, and my question was, what is the interaction landscape? Where do my sensors want to go? How much do my sensors talk to each other? And the way you can play around with that, you can notice that, okay, I have expressions that looks like log of 1 plus x, where x is small, where this can be made small. And we know that log of 1 plus x, if absolute value of x is under 1, you can just expand it as a power series. And maybe do some sort of fine manipulations with it. So the idea of this derivation is you assume you decompose this addition, this G times G transpose, as diagonal component and off diagonal component. Then you assume that your amount of noise on the sensors is large. So eta is large, which means your addition gets arbitrarily small. So you get into this sort of series convergence radius. And then you expand this power series in powers of 1 over eta. And then you rearrange the terms in a clever way and sum the series back to infinite order, but in some sort of different function form. And then you can extend the validity of eta back to arbitrary value. And if you go through this manipulation, you find the expression that my energy, so my target objective that I'm trying to optimize, has a constant part plus a part that is linear in the number of sensors. well, sum over sensors that I selected, plus sum over pairs of sensors, and so forth to higher order terms that we hopefully can truncate away. And both of these landscapes, both H and J, are directly computed by the data, computed from the data, computed from the SVD that we got. And the first part is this, what we call sensor one body energy, or physicists would call it external field, means my sensors are attracted to high variance locations. So if gi.gi is large number, then H becomes a very negative number, and you want to live there. The other part, J, is sort of like a measure of correlation between sensors, which means sensors are repelled from locations that they have high crosstalk with high correlations. This one was ugly, like hard to look at, unpleasant. So let's turn them into some pictures. So let's say I have my training data library. Here's my sea surface temperature data set, and I just vectorize every snapshot, and I split it in test and train as one usually does. And I compute my landscapes and pictures. I get it look like this. So to leading order, so my 1-point landscape tells me what are the locations with high variance of data. Where would I like to place sensors? And note, I didn't tell my my algorithm anything about like ocean physics or anything about geography of our world, but it automatically picks out certain locations, and you can see that it kind of gets darker around the coast of the oceans as opposed to the middle of the ocean. It gets darker in inland bodies of water, like the Black Seas, the Baltic Seas, the Great Lakes in North America. It also gets pretty dark around El Nino, which goes right along the equator from the coast of South America westward. And then the interaction landscape, the J landscape, we can visualize it in a sort of conditional way. If I place sensor in one place, how much crosstalk does it have with different locations? How much do I penalize other locations? And you can see that this sort of repelling is kind of fairly local phenomenon. So if I put a sensor somewhere in North Pacific Ocean, close to where we are now in Seattle, we probably don't want to put more sensors around North Pacific Ocean, and similarly with North Atlantic Ocean and so forth. And you can do this, use the sensors to compute a reconstruction and just ask, how good am I? What is my reconstruction error at every point? You can also compute reconstruction uncertainty. What is the error bar? Very similarly to how I did Bayesian inference previously, and to see where my sensors want to be placed, and they precisely are attracted to the locations that I mentioned, so continental coasts and inland bodies of water, and are repelled somewhat from each other, so they don't all want to cluster in the same place. They want to measure different locations around the world. And we see this sort of funny trend that the error of my reconstruction first goes down as I crank up the number of sensors, and then it goes up, and has my reconstruction is somehow very unstable when the number of sensors matches the dimension of the model that I'm fitting. Sits right around 100, and then it goes back down, and that is kind of parallels to well-known phenomenon in machine learning called double descent that we're currently working on. And you can play around with sort of the different benchmarking of these reconstructions on different data sets, and we show that our sensor placement algorithm is basically as good as algorithms that existed before, but we have these layers of interpretation. We now know why sensors want to be in certain places and how they, roughly speaking, interact with each other. And we started playing with this double descent question, basically to ask, when do you have this peak at 100, and under what conditions does it disappear if you're kind of very smart about regularizing your reconstruction? And that will be, that's in preparation, that will come up a bit later. So the outlook here is that using a prior on your coefficients in reconstruction improves reconstruction quite dramatically, and the sensor location can be to very good approximation understood as 1-point and 2-point interactions. Reading methods for placing sensors are fairly good, and we can use 25 sensors of sea surface temperature to predict the rest of the image, 40,000 sensors, to right without 1 degree Celsius, which I think is quite remarkable how much compression you can achieve here. And of course, we want to look at more things like double descent and combine this data-driven consideration of sensors with data-agnostic things to do design. We can do nonlinear reconstructions, we can do moving sensors, and so forth. So if the kind of stuff that I told you sounds like fun, I'm starting a faculty position at University of Hawaii at Manoa in Honolulu and mechanical engineering. In January 2025, I will be hiring for master and PhD positions. So you can read my website or shoot me an email to talk about it. Here's some tag words of things I work on that are not only things that were in the stock. And here's our money shot of our department recruitment. This is the conditions of things, which are very sad and depressing, especially if you look out the window now. So on this, I would like to acknowledge my wonderful collaborators here during my time at Washington. Lots of people we have discussions with. Lauren, who keeps the whole institute running. Our funding from NSF, AI Institute and Dynamic Systems, and the color maps I use and the font I use. And I will stop here and take questions. Thank you.
Great way to finish. The big slide of Hawaii.
I have to do it for next year or something.
Do you have a question on Zoom or can I ask?
No, you,
Doris, can you monitor questions?
no, you,
Okay,
it's
because I
it's
see
clear.
that there's like 25 messages on Zoom now.
Oh, no, it's about sound. Everything's about the sound.
Hopefully it got better. Yes.
So you showed back to Cindy, you showed the systematic error of the estimation of the coefficients, the mean of that. The scales proportionally with the discretization time steps squared. So basically, the free energy gives you which coefficient set to pick, like which subset to pick. But those expressions on the previous slide for the covariance and the mean estimate give you the actual values of the coefficient.
Yeah.
So does that mean in our experiments with Cindy that the values of the coefficient scale roughly with the size of the time step? Should we expect to observe that?
So if you look at this expression, so you see the covariance matrix C and the sort of covariance vector V, and both of them are computed by adding up over all of the data points. So V scales with the amount of data. C also scales with the amount of data. If you want to estimate what mu is, it's C inverse times V. So the scaling with the amount of data actually cuts it out. Right? Whereas the previous thing right above, the covariance for the confidence interval is just C inverse. And if C grows with the amount of data, then C inverse goes as 1/n. Right? So for the estimate of the mean converges pretty fast. Basically, early versions of this figure, I also wanted to plot what is my estimate of the mean against the amount of data. But that converges incredibly fast. And you can see this later in uncertainty quantification, basically how, like if you just look at how the mean changes, you can see that it jumps pretty fast. Note that on the right, all the horizontal scales are logarithmic. So your mean converges to a steady value fairly fast. And then, yeah, then just confidence interval keeps shrinking. And the amount of error is given by how bad your derivative is. A simple way to think about it, if you didn't have noise and you were trying to, if you don't have noise, then every single nonlinear function in your library, you know exactly. Like it's not affected by noise. Whereas your x dot, you know it with the error up to like order delta t squared. Right? So if on the left-hand side of regression, you have error of delta t squared, like your it's like the dependent variable is known with an error, your independent variables are known exactly, so then your coefficients are going to inherit exactly the same amount of error.
That's a cool result.
Yeah, I don't think anyone really showed it before.
So now you know exactly how the discretization type stuff influences
Yeah.
the discrepancy, the coefficients you're supposed to identify.
Yeah, and it strongly depends on how exactly you take derivatives. And maybe it can get much better scaling if you use other forms of taking derivatives. You can integrate it with weak form. Yeah.
The 1 point and 2 point methods seem analogous to actuator placement as well, not just sensor placement.
Yeah, there's like fundamental duality between sensing and actuation.
Yeah, do you see any differences when applying your technique to actuator placement that might differ from sensor placement?
Well, I haven't been applying it to actuator placement because that was not sort of project scope that I was doing so far, but I imagine it would be fairly similar. And I also want to, again, emphasize that numerically, all of this is incredibly similar to QR pivoting. So when in QR pivoting, you're trying to pick your very first either sensor or actuator, you look for like the row of the matrix that has highest delta norm. That's your first pivot point. That's exactly the same thing as on a 1 point landscape. Except for QR pivoting, you're like prescribed to follow this deterministic procedure. You always pick argmax, then pivot, pick argmax, pivot. The point of pivoting is that you want to orthogonalize yourself from the previously selected pivoting points. And I basically wanted to know, can I just stare at the original data matrix and extract landscape from there before I start messing with it? Because in like QR procedure, after you pick the first point, you change your data matrix. After you take second point, you change your data matrix. And I think some interpretation gets a bit lost. And also just replacing, argmax with like a softer decisions that like, oh, let me instead of just strictly the max, let me take a pretty good one. And that allows you to sort of relax the determinism. So determinism test. Yeah.
So at one point, you mentioned the realization of noise is more important than the magnitude of noise.
In
The previous issue.
yeah. So the question is about realization versus magnitude of noise. So the way to clarify it, so I have this ranges, right? For every other set. So all the sets are like free energy is shifted with respect to the baseline. So the baseline free energy always stays 0 here. Free energy of any other set has a range, and here this is not even standard deviation. This is just minimum and maximum across 10 realizations. And this is free energy per data point. And if I were to crank up the if inference very confidently returns to you which set has lowest free energy. If my target free energy competes with an interval, then which one is lower? Well, that depends on realization. Where exactly in that interval do you lie? Right? That's when realization of noise is important. But if you crank up the amount of data, the length of trajectories, then this interval itself shrinks. It would keep roughly the same mean, but it would shrink. So if I had infinite data here, then all of this sort of competing other sets from sort of quasi intervals, they would collapse into deterministic curves. But eventually all of those curves are going to cross over the free energy of the correct set. And so eventually my inference is going to break. So this like, under what conditions does the magnitude of noise matter is when your data is not infinite. Yeah.
No questions? Let's thank Andrei and Jim.
Thank you.